Hey everybody, and welcome to our last video in our first unit in AP Chemistry. And we're just finishing off these periodic trends that we started in the first video. So you might remember that we started talking about Coulomb's law, and Coulomb's law is like the basis for a lot of things dealing with periodic trends. Coulomb's law states that the opposite charges attract one another, and the higher the charges are, the more strongly they will attract one another. So, for example, if I have two particular particles, ones that have a +2 charge and a -2 charge, they more strongly attract one another as opposed to two particles with a +1 charge and a -1 charge. That's what we mean by that they have a higher charge to them. Secondly, Coulomb's law also says that the closer particles are to one another, the more strongly that they attract each other. And that is the basis behind a lot of the ideas dealing with ionization energy, which we talked about in the last video. Ionization energy is not something that we talk too much about in Chem 1, but something that we do talk a lot about is electronegativity. And we talk a lot about electronegativity dealing with bonds. So why do ionic bonds form between metals and nonmetals, whereas covalent bonds form between two nonmetals? It all comes down to electronegativity. So just to reiterate, because we did talk about this quite a bit in Chem 1, electronegativity is the ability of an atom to attract electrons to itself. The ability of an atom to attract electrons to itself. And you might remember the most electronegative element. So here is just a periodic table that contains this Pauling electronegativity values. These are just values that were assigned as to how bad particular elements want electrons. And you might remember seeing fluorine, where fluorine is the most electronegative element. So we know fluorine right here as the most electronegative. And that means that it wants electrons more than anything else on the periodic table. And there's a particular reason for that, which we're going to get into when we talk about these group trends here. Least electronegative elements are actually your noble gases. These guys don't want any more electrons because they're already stable the way that they are. They have that full octet of electrons that are surrounding them. We do have slight electronegativities, though, for krypton and xenon. The reason why we might see electronegativities here is because these can actually bond because these have empty d orbitals. So if you think about the electron configuration for krypton, its configuration, its noble gas goes from argon, right? So if I write argon in brackets, we'll just do krypton. We have argon. Let's see, it looks like we start on 4s2, 3d10, and it ends on 4p6. Now, in that fourth energy shell, we actually have electrons that can still fill other shells, because what's still not filled in that fourth energy level right here, you actually have your 4D that's totally unfilled. Because that 4D subshell is not filled up, that's why krypton and xenon can in fact bond like that. Argon can bond as well because we do have 3D orbitals that are empty, but not as common for argon to bond. But that's why you'll see some of these noble gases here that do have electronegativities. It's because it has empty d orbitals. Radon, I'm sure, can do that too. The reason why there's a dash there for radon is because it hasn't been studied that much yet. And that's because radon is not very abundant. Radon's also not a very good gas to mess around with. So chemists don't usually work with that one to test it out. Least electronegative elements other than your noble gases tend to be these alkali metals. These don't want to gain electrons. These would rather lose electrons. And that's because they have one valence electron, one or two, and it's much easier for them to lose those 2 electrons or 1 electron. Like we talked about in ionization energy, they have very low ionization energies. So I'll write this down here as well. Very easy to remove those electrons because that outermost electron or electrons are far from the nucleus. So that radius is very large. That electron is not nearly as attracted to the nucleus, and therefore they're easy to remove. So low ionization energy, low electronegativity. They don't want electrons, they want to lose electrons. Something like fluorine, that outermost electron shell is the closest to the nucleus, so it's more likely to gain an electron. Let's go ahead and just write these group trends down here. So let's go back to the text and get this stuff down. So if you just look at these values that have been assigned to the different elements, if I go down a group, right, you'll see that the electronegativity decreases going down. So let's go ahead and write this here. You'll see it decreases going down. Now, why would atoms not want electrons as much as you progress going down a group? Well, that's because you're adding energy shells, right? So hydrogen has only 1 shell surrounding its nucleus. Lithium has 2 shells around its nucleus. Sodium has 3, 4, 5, 6, 7. As you add those shells, the farther that outermost shell is to the nucleus, and Coulomb's law says that nucleus cannot attract an electron nearly as well. So that's because your valence shell is far from, or we'll say is farther from the nucleus. Therefore, the nucleus is, oops, keep spelling stuff wrong, is unable to attract electrons as strongly. All comes back to Coulomb's law. Let's take a look at this period trend as well. Period trend, as I go across, other than your transition metals get a little funny, and that's true for all the trends. But if we consider the main group elements, your main group elements are groups 1, 2, and 13 through 18 right here. Notice how, for the most part, electronegativity does increase going across, right? So if I look at period 2, let's say, it does increase. I have 1, 1.5, 2, all the way to fluorine. I do have a little exception there with the noble gases. Of course, the noble gases don't want electrons. They're already happy. So we'll say it increases going across. Of course, the exception is the noble gases. And the reason why is because as I add protons to the nucleus, so if you look, atomic number is going up by 1, and the atomic number for something tells us how many protons are in that nucleus. So if lithium has 3 protons in its nucleus, and it's in the 2nd energy level. But if I'm still in the 2nd energy level, but I add another proton when I get to beryllium, that added proton makes the nucleus stronger. And because it makes the nucleus stronger, Coulomb's law says it can pull that outermost shell in closer. When I add another proton going to boron, that particular nucleus will pull in that electron cloud even more. And when it pulls that electron cloud in even more, it can attract more electrons. So this has to do with adding protons to the nucleus. So increasing nuclear charge, which is otherwise known as adding more protons to the nucleus, attracts valence electrons more strongly. Not just valence electrons, but any electron. We'll say just attracts any electrons. Attracts electrons more strongly. And those are our trends for electronegativity. What I would just recognize, the fact that fluorine is the most electronegative. As you start to get farther away from fluorine, the less electronegative they are. In the same vein, let's take a look at atomic radius. And atomic radius is pretty simple. If you think about a radius, right, it's half of a circle. So it's the same exact thing for atoms. When I consider atomic radius, it's half, because it's a radius, the distance between two of the same atom are bonded together. Really nice images below, right here. Let's get the pen out again. Here it is. So let's say I have one hydrogen atom and another hydrogen atom. These are going to form a covalent bond in between them. When atoms bond, the reason why they bond is to lower their potential energy. So these particular atoms are going to come closer together until their electron clouds overlap. An orbital is a fancy way of saying electron cloud. So there's a nucleus right in the center of this hydrogen atom, and there's a nucleus right in the center of this hydrogen atom. There's a distance that those two nuclei are away from one another, but half of that distance is what we call the atomic radius. So it's half the distance between two of the same atom that are bonded together. And if I take a look at this really nice image off to the right here, this shows the atomic radius in units of picometers. I don't think it's listed here, but every one of these values is in units of picometers. Picometers. And as I go down a group, we see a very clear trend in atomic radius. And as I go across, I also see a very clear trend in atomic radius. There's really no anomalies here. It's pretty straightforward. So why would the atoms increase as they go down? Because clearly we could see that atomic radius gets larger as I go down a group. So let's go ahead and write it increases. Going down. And the reason why is because as I'm going down a group, I'm adding energy shells, right? Hydrogen has one shell around it. Lithium has two shells. Sodium has three shells around it. So once I'm adding those shells, I'm adding more electron clouds. So of course, those atoms are getting larger. So added shells around the nucleus. And not only do those added shells make it larger, but once I add those shells, the nucleus can't pull in those outermost shells anymore, because remember that distance is increasing. So added shells around the nucleus, we could say prevent the nucleus from attracting electrons as strongly. Then we'll talk about the period trend. So we could see here very clearly that as I go across any of these periods, the atomic radius is decreasing. Going across. Why would that be? Like we said before, all of these trends really relate to one another really, really well. So ionization energy, Coulomb's law, electronegativity, we can use those to explain atomic radius as well. As I'm going across, I'm adding protons to the nucleus, and those added protons, because of Coulomb's law, has a stronger pull on, in this case, the fifth energy shell. So therefore it pulls it in just a little bit closer. Once I reach the next element though, so when I go from xenon to cesium and I add that other shell, that nucleus can no longer pull on the seventh shell as strongly, which is why the radius then increases. And that's really why we call it a periodic property, or the periodic table, is because you'll see that I start off with some trends. It's hard to see for hydrogen and helium, but I have a relatively large lithium, decreases as atomic number increases, and once I hit another element, boom, it starts again. It gets even larger, and then that trend's going to repeat itself. And then once I go up in atomic number, eventually, boom, I'm going to see the trend repeat itself again. And that's why we call the periodic table, is because trends are going to repeat themselves over time. Increased nuclear charge, which, as you know, is the number of protons in the nucleus, pulls the electrons in closer. We're going to do practice with this in class too. So, of course, if you have any questions, please feel free to ask me in class. That is atomic radius. Those really are the three trends that we talked about in Chem 1. There's a new one though, and I think this one's relatively easy as well. It makes perfect sense. And this next one is ionic radius. So up above, we talked about atomic radius, where these are atoms that do not have a charge, but we also have ionic radius. Now this, of course, would be essentially the size of an ion, right? Or half the distance, half the size of an ion, because it's a radius. So it is the radius of a monatomic ion in an ionic crystal structure. So it's basically half the distance that of a singular ion that it has when it's in a crystal structure. So when it's bonded to something else, but in this case, it has to be in an ionic substance, so a metal bonded to a nonmetal. And I like this image a lot because I think it makes quite a bit of sense when you really break it down. So let's go ahead and pull this out again. So lithium, for example, lithium has 3 electrons, right? So lithium has 3 electrons. This is just elemental lithium right here. Now, if you think back to electron configuration, if lithium now has a +1 charge, so if it lost 1 electron, this lithium now has 2 electrons. Now, lithium is lithium because it has 3 protons in its nucleus. So I have 3 protons in the nucleus and 3 electrons. There's some pull that those 3 protons have on those 3 electrons. If lithium loses an electron, however, it still has 3 protons in the nucleus. Those 3 protons can pull on those 2 electrons much more because, again, the charge is not the same. The greater the charge, the more strongly they can attract. So if I lose an electron, that nucleus can really pull it in a lot more. Same thing goes for sodium. So sodium has 11 electrons, right? Sodium +1, if it loses an electron, that means it's got 10. Either way, there's 11 protons in the nucleus. When I lose an electron, those 11 protons can pull on that. So your cations are going to shrink in size. When an atom loses an electron, the number of protons outweigh those electrons, and your atoms are going to shrink. So we'll see here, that's the case for all of these cations right there. So let's go ahead and get this down in here. So cations, we have more protons than electrons, which causes the atom size to decrease. And that's because we have a higher nuclear charge. It all comes down to that nuclear charge. That's a really good phrase to use for a Unit 1 question. If we want to be really specific, we could say atom really slash ion, because if it loses an electron, it technically becomes an ion. The opposite is true for anions. So anions, of course, are negatively charged ions. So if I go back and we look at these two, fluorine has 9 electrons. The fluoride ion, however, if I have a negative charge, that means it's gained an electron. So the fluoride ion has 10. Either way, this fluorine has 9 protons in the nucleus, and this fluoride also has 9 protons in the nucleus. Because you add in an electron, those 9 protons cannot pull those electrons in nearly as well. So therefore, when you add electrons, the ion size is going to increase. So anions get larger because that nucleus cannot pull on all of those electrons as closely. Same thing goes for this next halogen, chlorine. So I have 17 protons in the nucleus and 17 electrons. I add that electron, those 17 protons can't pull them in nearly as much. I think that's pretty straightforward, as long as you really understand that whole, protons outweigh electrons or vice versa. So there are more electrons than protons, and therefore the nucleus is not strong enough to pull the electrons in as close. Remember, this all comes down to Coulomb's law. Everything in this particular section is Coulomb's law. Unit 1, I know I always say when in doubt, mole it out. For Unit 1 also, when in doubt, the answer is Coulomb's law. So has to do a lot with those charges, their radius and the magnitude of those as well. Let's do some sample problems together. So which of the following species has the largest radius? So just based off of electron configuration, we can identify how many electrons are here, and also how many protons there are as well. So sulfur has 16 protons. So this has 16 protons. And each of these has 16 protons. And that's by definition what makes sulfur sulfur. Now let's consider the number of electrons. So this sulfur is neutral. So this must mean that we also have 16 electrons. If I have a charge of +2, that means it has 2 additional protons than electrons. And here I have 2 additional electrons as opposed to protons. So which one of these does the nucleus not have as strong of a pull? Well, it's got to be this one. Those 16 protons cannot pull on those 18 electrons as strongly, and therefore that size of the sulfide ion is going to be the largest out of all of these. So let's insert a text box here, and we'll answer this question using some words. So we could say the sulfide ion. Let's go ahead and make this superscript. I'll use the fonts that I like to use. The sulfide ion has 2 more electrons and protons. As a result, the nucleus cannot attract the electrons and pull them in as strongly. Well, we can also say too, if we think back to orbital notations like we were looking at before, let's think about sulfur with a -1 charge. So this would be in the 3D block, so our configuration would be neon, and I would have 3s2, and I'd have 3p6, right? So here's my orbital notation. Here's 3s, here's 3p. And if I plug in my arrows, this is going to have 8 because it's stable. Another reason why we might see the radius increase is because these electrons don't want to be next to each other. Why don't the electrons want to be next to each other? These guys right here start to repel right there. Electrons don't like to be in very close proximity with one another. And if they are in close proximity, they do in fact start to repel a little bit. So we can also put that as an answer for this one right here. Either answer is fine, but I like to just kind of throw this in there because it's another contributing factor. Additionally, added electrons cause more electron repulsions within the electron clouds, leading to a larger radius. I like to just put that there because sometimes you might see a question that kind of brings back that repulsion thing, but ultimately I would always say that it's because those added electrons, the nucleus can't pull them in as closely because there's not nearly as many protons in the nucleus. Let's take a look at 15. So predict the trend in radius for the following ions. So I have beryllium, I have magnesium, calcium, and strontium. Notice all of these have a charge of +2. All of these are in the same group on the periodic table. They're all alkaline earth metals. So we can identify that on here. All of these are alkaline earth metals, all having the same number of valence electrons. These are all alkaline earth metals. So we really don't even have to consider the +2 charge because they're all +2. That's similar. All we have to look at is what's the relationship between all of these elements. And in this case, they're all in the same group. So what's the group trend? As I go down a group, atomic radius and ionic radius gets larger. And that's because I'm adding those electron shells, right? And adding those electron shells is, of course, going to make that radius larger because the farther away those electrons are from the nucleus, the more so the nucleus cannot pull them in. So in this case, we actually tend to be the same right here. It's already in order. Beryllium is going to be the smallest, and that's because it only has 2 energy shells that are around it. I'll put 2ES just to abbreviate right there. The next largest would be the magnesium ion, and the magnesium ion has 3 energy shells that are surrounding it. It's in the 3rd period. The next one would be calcium. Calcium's in the 4th energy shell. And strontium is the final one. This is in the 5th energy shell. I think I got to restart this pad or something because this thing is not looking very clear right now. Let's insert a text box and get some text in there so we can clarify that. So we could say that all these elements, all these species. A lot of times you're going to hear me say species. That's very common for College Board to use, even though typically you think of species in like animals, but these are technically species as well. Are located in the same group, all have the same charge. Therefore, the radius increases going down a group due to added energy shells. Like we said, we're adding those energy shells, so the atoms are getting larger, or the ions are getting larger. Let's take a look at one last trend, and this trend really kind of irritates me because electron affinity can technically be measured, because chemists can figure this out. And I'll just tell you what electron affinity is before I explain kind of why this irritates me. But electron affinity is the energy change that occurs with the addition of an electron to a gaseous atom. So it's sort of the opposite of ionization energy, right? It's the energy change that occurs with the addition of an electron to a gaseous atom. And because we're talking the energy change, we can quantify that energy change. We can figure out, right? Okay, well, what is this value? You could figure out the value for electron affinity as you can with ionization energy. The only thing is, nobody really uses electron affinity for anything. And I asked one of my professors, I was like, listen, what is electron affinity used for? Because it's in all these textbooks, and it's really not something that I've ever used. Even in my grad classes, nowhere. I was like, I had to brush up on electron affinity just for this little half a page. And basically, he just said that electron affinity is used in order to help come up with the electronegativity trend, because chemists can't determine the electronegativity directly. So even though all of these have electronegativity values, we can't measure electronegativity. They're just values that were given to elements based off of the values for ionization energy and electron affinity. I'm not sure if this is making any sense. Not that you really need to know this, but electronegativity is kind of something that scientists just came up with. It doesn't actually exist, but it's much more useful when we talk about chemical bonds. Electron affinity, personally, I don't find as useful. But I guess it does have its uses because it helps to kind of devise electronegativity. And it's kind of backwards from ionization energy, whatever. It's the energy change that occurs when an electron is added to a gaseous atom. So I have some elements in the gaseous state of matter. I add an electron. There is some energy change that is associated with that to produce the anion. And here's a graph of ionization energy versus atomic number. And here's a graph of electron affinity in units of kilojoules per mole versus atomic number. So we'll see here, and this is kind of confusing because we have some negative values right here. Hydrogen has a relatively high electron affinity. As I go down, beryllium or helium has a low electron affinity. So there is a negative energy change that's associated with that. When we have these numbers that are negative, or these values that are in the negative, if it has a negative electron affinity, that means it doesn't want to gain electrons. So something like helium it makes sense that helium doesn't want to gain electrons because helium is happy already in a pair. It already satisfies that sort of octet rule. It's got a full outer shell, not 8, still happy with 2. Doesn't want any more. That's why you'll see that this little section here is in the red, because these elements don't want to gain electrons. Beryllium doesn't want to gain electrons. If you consider its orbital notation, we have 2s and I have 2p. This 2s is totally filled. Half-filled orbitals or totally filled orbitals are more stable than adding another one onto here. So because this 2s is filled, it's pretty happy having just that 2s. It doesn't want to tack another electron into this 2p. So beryllium is also stable. This totally filled 2s orbital is more stable than adding another electron there. Beryllium has a negative electron affinity. Nitrogen's kind of on the edge, right? It's like, it's happy where it is, because if we consider nitrogen, remember, nitrogen is 2s2, 2p3, 2s, 2p. It's got 5 valence electrons. Nitrogen really doesn't want to gain an electron, because what happens if it gains an electron? I add an electron here, and electron repulsions start to become prevalent. And electrons don't like to be near one another. So if it could avoid that last electron, that's what it's going to do. Elements that are a little bit higher like to gain electrons, right? Or more, maybe not, they don't like to gain electrons, but they're more likely to gain electrons. Highest electron affinity, you could see, corresponds to fluorine. Fluorine really wants another electron because it has 7. It wants that last electron in order to become stable, right? So the higher the electron affinity, the more stable the atom is when it gains electrons. So like we said, fluorine gains 1 electron, becomes very stable. Oxygen gains electrons, becomes very stable. Nitrogen's happy because it's got that half filled, but carbon actually wants to gain electrons more than nitrogen does. So because carbon has a higher electron affinity, it is more likely to gain electrons than something like nitrogen, which is interesting. Trends, though, are not as evident here. They're kind of all over the place, which is why chemists tend to take a couple of different trends and make electronegativity, because electronegativity is really such a nice trend. Although, like we said, we can't measure electronegativity, but there are techniques and lab ways in order to measure electron affinity. Halogens have the greatest affinity because they really want electrons. Your noble gases have no affinity. And in fact, they are less stable when they add electrons because they don't want to get more electrons. This particular section on trends, and this video and the last video is tough, right? This is so conceptual. It's really hard to visualize periodic trends because we can't see them very, very easily. And that's what gives students a hard time with chemistry sometimes is, we can't always see these things with our eyes. And that's why it's going to take just lots and lots of practice for us to do. And if that's what it takes, that's what we're going to do to get us there. As always, if you have any questions, please let me know. You're 1/9 of the way through the course right now, so that's always a good feeling. And I'll see you in Unit 2. Bye.